All right. Good afternoon, good morning, good evening, wherever you may be. This is for 1A 11 in numerical analysis. So this is starting the journey through numerical integration. And I wanted to provide an example of the derivation of one of the formulas, besides just giving them to us to start playing with. And so this is what we're going to be talking about, the numerical quadrature and the derivation of the trapezoid rule. As mentioned in the notes, the approximation scheme that we're going to be using is building on the interpolation polynomials that we developed earlier. And so we're going to take our integral with our function f of x in between the intervals of a and b, or over the interval a, b. And we're going to suppose that the left endpoint is going to be equal to our value of a, and our right endpoint will be the n plus 1 node, where the x1 value is equal to b. And the difference, or the step size, is going to be the difference between the two endpoints, A and B. We only have two endpoints for this one, and so the most we can use is a linear approximation. And so we're going to use the Lagrange polynomial, but it'll be the linear version because we only have the 2 points. And so plugging in those values for P1, again, the linear approximation, we only have 2 points. We have x minus x1 over x naught minus x1 times the value of f of x 0, and then x minus x1 0 over x1 minus x 0 times f of x1. Okay, so that's the linear polynomial. So if we plug that in for the approximation scheme, we're going to get f of x over the interval from a to b is going to be approximated by the integral, replacing f of x by its approximation, these two linear values of x naught to x1 of x minus x1 over x naught minus x1 f of x1 naught plus x minus x naught over x1 minus x naught times f of x naught dx. Okay, and then we're not going to forget, of course, our error term. And so the trick to this then is to first, in order to know how well this approximation scheme is, we really need to find a bound for this error function, and we really don't know what this is. Okay. So this part will be easy to compute, but we first need to compute or understand, okay, what's happening with this error bound. And remember, I didn't notify it here or write the notation, but the sec of x here is actually a function of x as well. And so we really have no idea what's going to happen here. So we need to utilize some previous knowledge and recognize that on this interval between x naught and x, our value of x, wherever we're at in this range, the product of x minus x naught and x minus x1, it doesn't change signs. Okay. And that's really valuable because then we can say, by the weighted mean value theorem for intervals, we can apply this to this error term. So we can utilize this theorem to pull out this function of x in the second derivative and create it with and replace it with a constant value. Okay. So there is some sec in this interval, sec of x, in this interval that we're considering here, such that when we plug that value in, it allows for it to be a maximum or a minimum. It creates a constant value for the function to pull out. It's the idea of the weighted mean, right? And so this is giving us the image that always comes to mind is the area under the curve, and there's some value that creates the same average value as the actual area under the curve. And so that's what this point is. This is that sec. We can find it some arbitrary value in that interval between x naught and x1. And so we can pull that value out as a constant evaluated at f double prime. And that allows us then to reduce our interval to just a simple polynomial once we multiply out all the terms. So we multiply out each of the terms and then integrate. We get the constant term, and we get x cubed over 3 plus, well, minus x1 plus x0 over 2, x squared plus x naught times x1 times x. And then we're going to integrate between the two limits of integration. So if we plug that in and simplify, we get h cubed over 6 negative times the value here. And remember, h is equal to x1 minus x0. So thus the trapezoidal rule, or the approximation scheme that we're going to use for f of x on the interval from a to b, is going to be h over 2 times the midpoint, right? Basically the midpoint of those two. You may recognize this in a different form, but this is actually the area of a trapezoid. Thus the name. That's the reason why it's called the trapezoid rule. So this is like half the base times the base 2, right? So if you kind of think about it like a normal trapezoid, the x1 minus x2, that's the base. That's this. And then the f1 plus f2, that's like the average of the heights here, right? So this is the height. So it's base times height. So this is average value here, the 1/2. This is the midpoint basically of that. And so it's like the height of this trapezoid. And that's exactly what we're computing. And it has an error no bigger than h cubed over 12 times the value of whatever that seek may be from the mean value theorem for integrals. Okay, and so this is the final scheme that we would utilize then for approximating a function on an interval. Okay, so I hope that was helpful. I think it's helpful just to kind of get a sense of how these different numerical schemes are derived. We'll be exploring the Simpson's rule and the midpoint rule for the open and closed cases, and all of these have a general foundation in the Newton-Cotes methods. So hopefully that makes some sense, and you can play around with it. I'm looking forward to our next video, and I'll see you then.